All right, everybody, welcome back to chemistry. We are continuing on with our equilibrium and thermodynamics. Last time that we were together, we were talking about potential energy diagrams. So we know that there's certain things that are required in order for a chemical reaction to occur, and that typically means that they have to collide in some way. And then the last thing we looked at was we did a Google form and we were looking at how reactions don't necessarily have to go one way. Since the collisions have to occur and we know that they have to collide in the right orientation with the right amount of energy, we know that as the reactants begin to disappear and the products begin to form, those products can begin colliding and going in the opposite direction. And so our reactions can actually be reversible. And they'll do this, they'll start sort of switching and going back and forth until they reach something that we call equilibrium. Equilibrium is when the forward reaction is equal to the reverse reaction. Now, at this point, we're going to go ahead and flip over to notability, and we're going to see a reaction here. Now, in this reaction, we're just staying very simple. We're just using A plus B equals 2C plus D. But the idea is when we're looking at these chemical reactions, we have a situation where we start in the beginning. There might be lots of reactants, right? There's lots of reactants and there's none right here. And so we know that in the very beginning of the reaction, it's mostly going to be going in the forward direction because these are the only collisions between A and B that we could possibly get. But as this begins to dwindle, because we're using more and more of them up, we get to medium amounts here. And so my forward reaction is getting a little bit smaller. But what we're going to see now is we have a little bit here. We have a medium amount here, which means that these are starting to collide and we're starting to go in this direction a little bit. And so we're starting to get a reversible reaction. Now, at what point are these arrows going to be equal, right? It doesn't necessarily have to be a 50-50 mixture. Sometimes we saw in our previous videos that it could be something like this, 60-40. When we finally reach this point where the reverse collisions are equal to the forward collisions. It's not always going to be equal because remember our potential energy diagrams, right? When we look at a potential energy diagram, need to switch to the pen here. We might have a reaction that looks like this. So the forward reaction is easier than the reverse reaction because look at these activation energies, right? So in this particular example, if this reaction up above had a potential energy diagram that looked like this, odds are when this thing reached equilibrium, you're probably going to see something like this. 40% of those are left and 60% of those are left, right? Because in this situation, we're going to need a lot of these things to be present in order to get a good collision that actually has the right orientation and has this huge amount of energy. It's just not going to be as easy to go in this direction, so we would expect to have a lot more of those left over in the solution. Now, if I change this potential energy diagram up a little bit, and I see something that looks like this, now which direction is going to be easier? Well, we can see that the activation energy is easier here, so I would probably flip these things, right? And maybe we would have something like 40% over here and 60% over here. Because we know that going in this direction is going to be much more difficult. What if we see a potential energy diagram that looks like that one? Oh, now look at this. The activation energy in reverse and the activation energy forward are pretty close. So now maybe we're seeing something that looks more like this, 50-50, right? So it's all going to be the nature of the reaction, how these things change. And so when we're describing our reactions, sometimes we're going to see things that are really, really, really efficient. And we have things like this, 5% are left over here and 95% are left over here. Those are the best kind of reactions. They're the ones that we spend money on our reactants and boom, we get all that product that we wanted to sell or use for other reactions or whatever the case may be, right? That's the kind of reaction we like. Sometimes, though, we end up with things that are not good, right? Sometimes the reaction is opposite. Maybe it's like 95 over here and 5% over here. That's no good either. And so when we're describing these reactions, when somebody says, hey, is this a good reaction or a bad reaction, the way that we can kind of describe that is by comparing these amounts, right? Is there going to be a lot of reactant or a lot of product? And we don't want somebody to come up and go, oh, well, it's a 60-40 or a 35, right? We don't want these percentages. We just want one number that describes that. And that number that we use is called the K value. Now, there's this little EQ down here. We're saying that's at equilibrium. EQ stands for equilibrium. But I'm going to warn you right now, as we go through this unit, there are lots of K values. K basically means when is the reaction at equilibrium. And sometimes we change that subscript. You're going to see things like A for acids, and you're going to see B for bases, and you're going to see C for concentration, or Kp for pressure. But basically saying we're finding an equilibrium. The important piece that we see here is this capital K. Now, if we see that a K is equal to 1, basically what we're saying is that it's a 50-50 mix, right? If we see that K is, I don't know why this is a dot here. We're looking for a huge K. So if K is greater than 1, right, then we're going to say that it's the products that are favored. And if K is less than 1, we're going to say that the reactants are favored. And so the way that they come up with this value is really they just look at the actual quantities. They look at the molarities, right? So we're going to notice that you can only use gases and you can only use aqueous substances because both of those have molarity associated with it. So we could either use molarity or we could use pressure. That's possible as well. Pressure can be related to concentration. And what we do is K is comparing the products and the reactants. So it's basically the concentration of the products up on top over the concentration of the reactants down below. And so that's why when we see over here that if they're equal to one another, nothing's favored, because it would be like, hey, there's 10 of these and there's 10 of these and that's 1. Right? It's a 50-50 mix. Versus if we see something like the second example there, right? If K is larger than 1, maybe it's something like 10 of these and 5 of these, right? So all of a sudden my K value, 10 divided by 5, is 2. We can see there's way more products in this reaction. It's more favored. So the bigger our K value gets, the more products we have and the better reaction it is. So let's look at this with some real chemicals here now. If we're looking at these, let's take a look at iron and CO2 and FeO, CO2. So we've got this reaction happening here. And the first thing that you want to do is make sure that it's balanced. I don't think that this is balanced, or maybe it is. 2 O's, 1, 2 O's, 1 Fe, 1 Fe. Yes, this is balanced actually, okay? And so what we want to do is we want to say, all right, Keq or Kc or Kp or whatever they're asking, but the capital K is all that really matters, is equal to the concentration of products over the concentration of the reactants. And so if we were writing this out, remember that it has to be concentration, and so it has to be items that can give you a concentration, which is either gases or aqueous substances. And so we're going to take a look at my products first. We're going to plug those in on top. So my products, one is FeO. Now, if I'm looking at FeO, I would say that the concentration of this, can you have a concentration of a pure solid? Concentration is molarity, and that's moles dissolved in liters. This is not dissolving. So this guy right here, because it's a solid, has no place in our equation. But this one's a gas. That works. You can have a concentration of gas. You can have moles in a liter container. So you can actually calculate molarity of a gas. So we're going to go ahead and put CO up on top. And then we're going to go ahead and leave out the FeO. So now we're going to go down to the reactants. This one, once again, is a solid and can be ignored. And we're going to go ahead and have our gas on the bottom. And so this is going to be CO2. And then we would go ahead and plug in whatever numbers or values they give us. So let's take a look at something that actually has some numbers. Let's apply how this works. This is going to, I didn't write you an equation, but we could do that real quick. What is the equilibrium constant for nitrogen gas combining with, so that's N2 gas, combining with oxygen gas to form nitrogen monoxide? So we have two N's. We're going to balance this out. So this is going to be K is equal to the products over the reactants. So let's take a look at what my products would be. Now these were all gas, and nitrogen monoxide is a gas as well. So everything's a gas, so everything's going to fit here. So we're going to put NO up on top, and then on the bottom we're going to put N2, and then we also have O2, so it's going to be times O2, right? So basically everything is being multiplied and divided. Now there's one other thing we have to add here. In this particular equation, we have a coefficient. If you have a coefficient, that becomes a power. So since NO has a 2 in front of it, this is going to be squared. So when we go to calculate this value, we're going to have K is equal to NO, and NO is right here, so we're going to go 1.1 times 10 to the negative 5, and this is going to be squared. And then this will be over the nitrogen, so nitrogen is here, and this is going to be 6.4 times 10 to the negative 3. And then the oxygen is here, so 1.7 times 10 to the negative 3. And so we could go ahead and put this into our calculators. Let me see if I can pull this up really quick. All right, here it is. So we've got 1.1 times 10 to the negative 5. And we need to square that. Divided by 6.4 times 10 to the negative 3. Divided by 1.7 times 10 to the negative 3. And we get 1.11 times 10, two sig figs, 1.1 times 10 to the negative 5. Okay? So, with that being said, we can see that this is a very small K value, right? This is not going to be a very good reaction. Not a very good reaction at all. Okay? So let's go ahead and take a look at the next example. What would be the lead concentration if 2 grams of lead dissolved slightly in solution? So once again, they didn't give us an equation, but we could figure this out real quick. So PbCl2 is dissolving. So I put a picture over here. We can see. So here's some H2O, and this is some PbCl2. Now, in this particular reaction, PbCl2 is a precipitate. If you think back to your solubility rules, we know that not everything dissolves very well. Water sometimes has trouble pulling certain things apart, and we can see that PbCl2 seen on the bottom. This is what we call saturated. Remember that when something is saturated, the maximum amount that has possibly dissolved is in solution. If I put another scoop of this in solution, it's just going to sink right to the bottom. So it doesn't dissolve well, but water is coming in. So if we picture our Pb and our Cl and our Cl, right? This is my structure, Pb plus 2, Cl minus, Cl minus. We know that there have been a few waters that have come in and pulled that chlorine off, right? There's a few of them, maybe not a lot, but there is a few. We need to figure out how many, right? That's our goal here. They're saying what would be the Pb plus 2? And we could use this to tell us, because we know that if something is dissolving, if this is the equation and it's dissolving, water is trying to split this apart, right? So it's trying to get it into Pb plus 2 and Cl minus, and there would be 2 of those. This is a solid, and these are aqueous. So if I was going to write a K expression for this, it would be products on top over the reactants. right? And so in this particular problem here, we would say that this is going to be lead, Pb plus 2, and then we have a Cl minus, and then remember that 2 right there, that guy tells me that it's squared. Those are aqueous, over the PbCl2. Wait a minute, that's a solid. We leave it out. Okay, we leave that out. It doesn't fit in the equation. All right, so now we're getting somewhere. All right, so let's plug in what we do know. They gave us the K value. So in this last problem, I gave you the concentrations, and I asked you for the K value. All right, but that's not what's happening here. We're just working backwards. They gave us the K value, so this is going to be 1.7 times 10 to the negative 5. And we're asked to find lead. Do we know what lead is? No, we don't know lead. Lead is unknown. That's X. Well, shoot, we have a problem here. We don't know chlorine either. How do you solve this equation when you're missing 2 variables? Well, let's think about this for a second. If I have one of these lead chlorides and it dissolves, what's it going to give me? It's going to give me 1 lead for every 2 Cls. So if one of these dissolves and gives me 1 lead, and that lead is X, how much chlorine would there be? Well, if it's a 1 to 2 ratio, this would be a 2X. You'll always have twice the amount of chlorine as you do lead. So if this is a 2, you would have a 4, right? Or something along those lines in terms of what your X value is equal to. So let's see if we could figure out what that X value is. So we go 1.7 times 10 to the negative 5 is equal to X times, so 2 squared is 4X squared, which is going to be equal to 4X cubed. And so to get X by itself, let me get the calculator going here. We're going to go 1.7 times 10 to the negative 5. We're going to divide by 4 equals, and then we're going to find the cube root button, right? So we're going to have, basically it's 4.25 times 10 to the negative 6 is equal to X cubed. So we need to find that, right, cubed root button. And on my calculator, that is where? Where is this? I'm not familiar with this calculator here. Let's see. Shift here, answer. There we go. So X is equal to 0.016. Looks like we had 2 sig figs. I shouldn't have gone to 3 right here, but we have 0.016, and the units are molarity. Okay. So if you had something like NaCl, and this was dissolving, you'd have Na plus and Cl minus. This would be a 1-to-1 ratio. So when I was doing this, what would my X's be? It would just be X and X for this one. What if it was AlCl3? Right? What would we be working with in this one? This would be X for Al, and what would Cl be? 3X, right? And it would be cubed, because that goes up twice. So really this 3 is kind of popping up here twice. It pops up when we write the equation, then it also pops up when we plug our values in. So watch out for that. And as long as we can handle this concept, we're okay. So understand that some reactions are just better than others. And we describe how good they are by comparing our products to our reactants. The more products there are, the bigger the K value is going to be. We can only use aqueous substances in our equation, never solids, because we can't calculate the molarity of solids. They won't dissolve. They're not doing anything for us. So keep that in mind and you should be fine. Thanks, guys.